This is going to make life interesting.
But maybe you can turn it like this.
Yep.
Yeah, good morning. My name is Arndt Kern. Thank you for coming back for another exciting day. We are talking about instrumentation today, and our first speaker is going to be Pamela Whitfield. She's coming from the National Research Council in Ottawa, and she's going to talk about laboratory instrumentation. Pam, please.
Right, thank you very much. I'm afraid the remote mic doesn't work, so I'm going to have to stand here. Right, I'd like to thank the organisers for actually inviting me here. It's a very kind invitation. It should be on. But these give me a bit of a dilemma, as in laboratory powder diffraction, you could actually spend a whole day talking about this stuff. So, as in, what to talk about? Well, most people know laboratory. One's on. This one says it's on, but maybe I ought to sit down. Right. Most people do sort of like their first experience of powder diffraction is always, well, usually the laboratory instruments. Now, many times laboratory instrumentation tends to be an exercise in compromise, especially in many departments where effectively everybody's sharing one instrument. You're never going to please all of the people all of the time. Now, as I say, you could actually spend a whole meeting doing, half a day sample prep. It was quite easy to cover. There was quite a lot of really basic stuff. However, this actually is a meeting about the power of powder diffraction, so we're sort of like not really going to cover the real basics are covered by quite a few textbooks, so going over that one would be sort of like a little boring, so we'll try and do some other more unusual things. This might be a little strange. I'm going to do a couple of considerations when buying or configuring an instrument. It's actually very common when I actually find a university department has bought an instrument and they've actually bought the wrong one. Because I haven't actually thought about what they needed before they actually bought it. So they got a standard instrument which doesn't suit their purpose. Fluorescence, which is obviously, for anybody who has to deal with it, is one of the biggest, it's basically a nuisance. Sort of like, if this is, it's something that many people have to deal with, and some of the things that you can do to actually reduce or avoid it. And then there comes the interesting stuff, which is seeing how far you can actually push laboratory instruments if you give it a bit of thought. If you're actually buying, I know many of the students sort of like currently won't be in a position, but many people may find themselves in a position of actually buying an instrument. Now, really sort of like, rather than, when you're actually sort of doing this, or even just finding add-ons to actually configure an existing instrument, actually try and understand the instrumentation, not just in terms of what its capabilities are, the characteristics, and actually whether it's going to do the job you want to do. Be precise, otherwise you can end up with something that's not fit for purpose, and preventing the problems is a lot better than trying to fix them afterwards. I've actually had to try and help people sort out issues they've had because effectively they bought the wrong setup. And sort of like, and this is sort of Star Trek quote, you cannot change the laws of physics. A lot of the problems with laboratory diffraction, they're fundamental. If you get something wrong, there's not always an awful lot you can do about it without a considerable expense. A lot of this issue comes to matching the instrument to either the sample and or the actual application. Now we'll come into this in shortly. Anybody doing functional materials especially, I'll come back to this, but fluorescence is a serious issue. So any functional materials are often, transition metals are in there. Some elements are actually worse than others, and I will come back to this a little bit later. Are your samples low absorption or high absorption? Now, this is a particular issue with multi-use instruments because ideally, if you're actually configuring the ideal instrument, the actual requirements are completely opposite. If you've got a low absorbing sample, ideally you want to be using transmission, or if you've got some such a thing, a parallel beam instrument, sort of like a lab instrument, which you can get these days. Or if you've got a high absorbing sample, such as a lot of the ceramics or sort of like, I don't know, yttrium stabilized zirconia, a lot of the battery materials, then it's actually a reflection geometry is actually quite sufficient. Small samples, this is actually something that crops up a lot. People have a very valuable sample, they've only got, say, a couple of hundred, 50 milligrams of the stuff. What do I do with it? It's actually a very difficult problem. Ideally, sort of like you could use capillaries, although that's, absorption is an issue, so if you've got a small amount of a highly absorbing material, it can be an issue, but that's actually something that will crop up later in the presentation. Or you can buy dedicated micro diffractometers, but then again, sort of like on a multi-use environment, unless you've got money for a second instrument, not always possible. There are a couple of tricks that you can try to do, and if you've got particular problems with small samples on lab instruments, if you come and talk to me, I'll try and push you in the right direction. It's a difficult problem, but you can't get around, you can't actually avoid it entirely, but you can actually reduce the issues. Morphology. This would be plating materials, soft materials. For instance, if you've got materials that can't be ground for any particular reason, again, and this will cover up a number of times, capillary stages are actually very useful. If you're actually getting an instrument, it's actually useful to add a capillary stage onto your into your purchase, even for later use. Now, sometimes you might actually find that the requirements of the sample and the requirements of your technique don't always quite match. And this sort of like starts becoming a little bit of a compromise in itself. I think we heard from Peter, that sort of, Peter Stevens yesterday, that for indexing, the peak positions are what you really need. For instance, with the low absorbing samples like organics, for the quality data for refining and structure solution, and you actually ideally would use transmission data, but if you actually want indexing, if you don't have transmission data, the intensities are important, so you can get away with thin plate reflection. In many instances, you find that a single experiment is not really sufficient for all the techniques you're going to be using. In some instances, you may need to collect 2 or 3 different data sets, depending for the particular technique that you want to use. So in some instances, one data set for indexing for particularly good peak positions, and then extra ones for, say, the structure solution or refinement or anything else. One that comes up, high temperature or rough samples, that's something where parallel beam instruments actually do tend to come into their own. Something to think about. Mirror optics, they're not cheap, but sort of like they are available these days. Pretty much all the vendors actually do offer them. Now, fluorescence. Said this particular problem with multi-use instruments. You probably already know this effectively happens when the radiation you're using is being absorbed by the sample and re-emitted. So what effectively you're doing is taking intensity away from your peaks and basically dumping it into the background. So it's basically taking away what you want and putting it where you don't want it. The common issues in terms of the most common tubes, for copper radiation, you're really looking at sort of cobalt's really nasty. Iron is one that crops up very frequently. Manganese, sort of like can cause a few problems. With cobalt, the really bad ones would be manganese, chrome, and titanium. Now, you may notice that manganese actually crops in both of those. That's a particularly nasty one to have to deal with if you don't have some kind of way of dealing with it. A consequence of the fluorescence is you get noisy data and your peak to background actually suffers really badly, can be very poor. And for anybody who hasn't actually read the Whitfield refinement guidelines, which Lynn McCusker sort of published, I can't remember how many years ago, he will actually go into this, and generally speaking, sort of like peak to background of around 50 is actually sort of desirable for sort of trying to get particularly accurate results from refinement. Some of the techniques, it might not matter quite so much. And ironically, some of the more modern, sophisticated setups can actually be more problematic than older instruments. PSDs, in many instances, you cannot use a secondary monochromator. So this is worth thinking about if you're actually got an instrument. If somebody comes along, you've got a system set up with a nice PSD detector and copper radiation. If you have people in your department, for instance, working on iron oxides, cobalt systems, some people will be very, very happy with their count rates, but the people working on those particular materials are going to be extremely unhappy because their data is going to be pretty bad. What can you do about it? If you're lucky and you have the time to do it, you can change the X-ray tube. This is the most effective way of dealing with it. You can say here, this is actually a manganese-based spinel. And sort of like here we can see the copper, which is your common one, is not particularly wonderful. And this was a PSD, by the way, so there's no monochromator. The cobalt is really bad. And this is actually, unfortunately, our routine setup currently. So I'm actually having to actually take some steps for the people who are doing cobalt systems to actually try and reduce this problem. Moly may not be very common, but that actually sort of really avoids a lot of the problems. This is a bit of an oddity if you use chrome. This is one of the sort of like ways around you can actually get particularly good data from a manganese sample, but again, there's a compromises involved. You're sort of like your low resolution in terms of despacing starts to suffer. Right, this is basically the selection you've got to choose from. Most common, not always the best though. Many instances, people actually get a laboratory instrument and automatically that's what they get. So it's actually worth asking yourself whether that's actually the right one for the job. Cobalt is probably the second most popular. This is actually what you'll tend to find in most mineralogy departments. A lot of their materials have iron in, so sort of like it's actually enough of a problem, often enough, that they actually think about these things. And then you've got some of the slightly weirder ones. Chrome's often used for stress, but as I say for manganese, it's actually does avoid some of the problems there. Moly, it used to be very common in very old, even older than me, days, that sort of moly powder instruments actually did used to be relatively common. They died out to some extent, but now they're coming back. You'll often find these tubes lying around because it's single crystal, tends to use them all the time, so they're quite easy to get hold of. Iron, it's a pretty rare one. I actually only know one group that uses that. Tends to be quite low power, but sort of like it's been used for some capillary work with manganese compounds. It doesn't fluoresce and actually sort of like doesn't scrunch up the pattern the same as the molybdenum does. Silver. This is again is a pretty odd one. It's pretty exotic and often quite useful for things like doing PDF work where you actually want to get to high Q. This is actually, practically speaking, the highest Q range you will be able to get for PDF work in a lab is using this particular tube. And also you've got penetrating power so you can actually start punching through materials for non-ambient cells. And I'll be showing an example of that later. If you can't change the tube, now what? It's old-fashioned, but it still works. The secondary monochromator does a pretty good job of actually stripping it out from the background. This is actually a secondary mirror, but it's pretty much the same thing. You'll find here you get very noisy data, high background. With a properly strip out that fluorescence, that's actually a real peak, actually in a spinel. And sort of like here, you actually wouldn't be able to pick it up. You can compensate a little bit by counting for longer, but you still have issues with your peak to background, so it's not ideal. As I say, prevention tends to be better than cure. One thing that's worth considering also is getting an energy discriminating detector. The Brochure version would say with a Sol-X, which actually electronically gets rid of the fluorescence. So you don't have a monochromator there. However, if you've got a PSD, for instance, I believe the accelerator you can get with a monochromator, but in many instances, you're pretty much sort of stuck with reducing the problem but not eliminating it. Now, people don't often look at these. There is such a thing if you look in your configurations, detectors have what they call discriminators. And this is basically the electronics deciding which part of the energy spectrum it's going to count and which part it's going to effectively ignore. And here we've got the effect of tightening the discriminators with cobalt radiation on this actual manganese spinel again. And you can actually see here, if you actually have the discriminator effectively wide open, so sort of like, so you're just taking the whole of your peak and all the background that's coming with it. Peak to background is about 4.2, which is pretty horrible. Here, peak to background is 4.5 if you actually tighten it up a little bit. Tighten it up a little bit further, and you actually start getting something that looks a little bit better. Now, these actually have been, these peaks have been normalized to the background. So the one thing you don't see here is the fact that you do actually suffer quite considerably in terms of the counts that you get, because you actually end up throwing away quite a significant amount of what you do want, along actually with the background. So it's very much a trade-off. So it's actually worth spending a little bit of time finding the setting which actually produces the best peak to background whilst giving you quite, as good a count rate as you can actually get. Now onto something which might be a little bit more, as I say, beyond the sales brochure. Everybody has these nice glossy brochures, but really at the end of the day, the interesting stuff is non-standard. Basically, something that you actually have to bring a bit more thought to bear rather than doing it the standard way. If you actually run a lab yourself, you'll often find people will give you fairly unusual samples. And sort of like, if your instrument would normally not be able to deal with it, how do you cope with that? In many instances, send them to a synchrotron, which in many instances that's, what you will end up doing, because there's just no way, however imaginative you get, of actually dealing with it. Or, let's say, use your imagination a little bit. Roadrunner. In this particular instance, you don't have Acme Company to come to your rescue, so you have to come up with some of these ideas yourself. But really, to do this kind of thing, get to know your diffractometer geometries. Each geometry has their own subtle characteristics. Detectors have their characteristics. So you actually understand properly what your instrument's doing. Sort of like not just what it produces, but how it goes about it. Optics, monochromators, mirrors, monocaps, polycaps. There's a whole range of different optics that you could bring to bear on this. Detector design capabilities, be it PSDs, silicon strips, gas detectors, scintillation detectors. There's some different ones to actually choose from. And also, this comes into play quite a lot, the absorption transmission properties at different energies of the sample that you're actually looking at. Many instances, if you're very lucky, a very good design on fabrication shop comes in very handy on occasions. And if you're actually going to build something custom, it's often worth bearing in mind before you buy the equipment that you may have to integrate it with the manufacturer's systems, and it's worth considering this before rather than after. If you buy a temperature controller or some other thing, make sure it can actually talk to your diffractometer computer before you buy it rather than after. And this is actually something that becomes a little bit more tricky. In many instances, synchrotrons, you've got a little bit more space to play with. On a lab system, you actually do have weight and size constraints. For instance, make sure you've got sufficient clearance so you're not crashing optics sort of every 5 minutes when you reference one of the arms. And this comes up a lot. It's always the nasty little practical stuff, i.e. you've got a screw, and have you got enough space to actually get the screwdriver into it? It's sort of like little practical things that will actually trip you up. Now, high energy X-rays. I believe Robert Dinnebier is going to cover some of this in his presentation later in the week. And it is actually something that's actually very useful and is actually becoming more popular. Now, the one thing that does crop up with high energy systems more than, say, copper, cobalt, or any of these other ones, is if you actually use a beta filter, you do get these rather nasty artifacts. Basically, the absorption edges from the beta filter do start doing some rather weird things. Absorption edges, sort of like little tails here, there, and everywhere. So, and it's pretty difficult to fit on a conventional basis. Oops. Now, ideally, if you've got the opportunity, basically if you use a primary beam optic, that problem disappears, so you don't actually need the beta filter. However, if you don't have that opportunity, for practical reasons or whether sort of primary optics can be rather pricey, I think I've got a quotation for a molybdenum mirror, which is about something like 70,000 Canadian, which is quite a lot of money. If you can't do that, you can actually start playing around a little bit in your refinement with your emission profile. Now, you can actually start doing that on a very empirical basis. This is actually using Topaz, so it's actually a little bit easier to do this. I'm sure a lot of the other software you could play around with this a little bit as well. Or you can actually use a custom function, which actually, unfortunately, isn't available in the current version of Topaz, but will be in the next version. So you can actually do quite a respectable job of actually fitting these. The peaks still look pretty ugly, but sort of like you can actually get a reasonable fit. Now, this is one of the applications for high energy. This was a new mineral that somebody sent me. Very, very small sample. So this is one that's really a capillary issue. Lead, as anybody would know, has a pretty high absorption. So normally you would think not transmission. So you've got two sort of like contrasting things there already. This would sort of like my copper sort of capillary system. I think the transmission through this would be, it'd be like a brick wall. It just wouldn't do anything. So, first impression, send it off to a synchrotron, nice beam line, high energy, no problem. Okay, right, I was told, no, we don't want to send this to a synchrotron. The reason being, this was originally going to be called Cranswickite. Somebody beat us to it, but anyway. So they wanted to do it on a lab system. So, fair enough, sort of like, now, what equipment do I have available? Well, I do have a capillary stage. Now, for this kind of thing, smaller capillary as you dare use, I'll say WIMP here because really I should have used a smaller one, but this is such a rare sample that if I jammed it in a capillary, I would be spending half a day under an optical microscope sort of trying to recover it. So yeah, I wimped out, I only used a 0.3. Highest energy X-ray tube I'd got. In this instance, it was moly. I've actually got a silver tube now, but at that time I didn't. Unfortunately, for my moly, I don't actually have any primary optic, so I had to try this on old-fashioned divergent beam capillary, which is sort of, it's not something I sort of like my ideal particular experiment. The resolution and intensities aren't going to be wonderful, and if you work out the theoretical absorption even with moly on a 0.3 capillary, the absorption is still pretty high. So, but you'll get actually a little bit of data to see what it looks like. And this actually is some of the data, and this is basically search match result. So, not wonderful, but good enough to say we actually found out actually that it was basically a mineral analog of a synthetic lead fluoride, and not single phase either. It's got an awful lot of tin oxide in it, which again, that's not wonderful news as far as absorption is concerned. Next step, ask for help. You know, sort of like people out there do have other instruments. You don't necessarily have to stick with your own one. If you have a little network of people who maybe have some more odd setups, find somebody who's got a focusing silver setup. I happen to know somebody who's got a focusing silver setup. The folks at Brochure were playing around with silver for doing PDF work, so they actually had a system already set up. So I sent it off to them. And they've also got a customized PSD for the higher energies, because silver is a high enough energy that sort of like, you know, most PSDs, you know, sort of like won't even pick it up. It's sort of like, or even if it does, the actual efficiency is going to be horrendous, because most of the radiation just goes straight through. So there are such things as customized ones, and this is basically, you know, Whitfield fit of these two phases, and this is yet another. I've got some data to work on this. Another unknown mineral phase, which actually was just doing a bifit. No beta filter artifacts, because there's there's a primary mirror there, which is effectively the same as a primary monochromator. Sorry. A 0.3 millimeter capillary again. This time you've got. This is a little rule of thumb. I like to see. Mu r, which is mu's linear absorption coefficient, and r being the radius of the capillary. I generally like to see that below 3, because a lot of absorption corrections sort of like can't really cope that well with high absorbing in data sets. So it's nice to get that down to a sensible value. I'm going to say multi-phase, but with sort of like modern software, you can actually deal with that. That's not a horrendous problem. Now, we'll just compare the two data sets here. Top one here is my moly data, using sort of like a pretty rough and ready divergent beam sort of setup, you know, molybdenum sort of like, and this is the silver. Now, obviously, the silver is better, definitely. It's also quite nice to pick up some of the lower angle reflections. But the same basic features are there. However, what this doesn't show is how long this moly dataset took to get. Because with a divergent beam and a capillary, sort of like you're losing an awful lot of radiation impinging on your capillary. So the intensities you get are not good. So you end up counting for a very long time. Another high energy application would be PDF in the lab. You're never going to get anything as good as the synchrotrons, but you can actually have a go. You can maybe sort of get an idea of what's going on before you send things to the beamline. And in writing proposals, it is often handy to say that you actually have given things a try in the lab before you actually go to the synchrotron. So you're not wasting their time. You actually have some data that give you an idea that the experiment's actually worth doing. Now, if you take this particular material just as a normal Whitfield fit, it was a multi-data set one, but this is the copper one. It actually fits really nicely. Disordered metals, you know, bond distances are all nice and equal, sort of like. But here you've got sort of like manganese 4, nickel 2, cobalt 3. Theoretically, the bond distances here are actually quite different, but here the disorder is such that they look the same. Now, you know, 145 degrees here with moly, sort of like you're getting to fairly sort of low D spacings, you know, reasonably high Q. I can't remember what the limit from that is. It's about 17 inverse angstrom, something along those lines. And sort of like, you know, you can get the data. It's actually worth using a PSD because PDF usually wants particularly low noise, otherwise you get sort of like you know, artifact problems. Cover that. And there's sort of like, obviously, the resolution of the actual function is not going to be wonderful, but it's good enough to show you actually do see, this is a model of the sort of like of the random distribution, and this is actually the experimental data in the back, and you can see it splits. So basically all I've done here, I've only replicated what has been done previously on a synchrotron, so this is already known, but you can actually replicate it in a laboratory system. The data is not going to be as good, but you can do it. Now, onto something more dangerous. I'm not actually out to sort of like, you know, insult people on this. I use gas pressure rather than hydrostatic pressure, so basically I build effectively bombs. If these things fail, they go bang, you know, very loudly. This is the kind of thing, sort of like, so you get into pressure vessel territory here, which is particularly nasty, but this one's 125 bar pressure. You know, built to look at polymer crystallization with high pressure CO2, which goes supercritical, so therefore you get, it's effectively got the density of water. So you've actually got to punch through quite a lot of material here, both sectional windows to actually hold the pressure, and sort of like the actual material on the inside. And here you can actually see, in terms of a theoretical calculation, what your fractional transmission is with CO2 pressure with the different energies. And you can see here that sort of like with, if you used copper radiation with this, you're sort of like start not too bad and it, you know, sort of steadily gets worse. And all of a sudden your CO2 liquefies, bang. Basically you got nothing. It just sort of like, you get nothing at all. Moly, you still get a little bit. So silver, which I didn't have at the time, it's actually not that bad. You're looking at sort of 50% transmission even through all this junk. So it actually has some use. Time resolution. This is another thing that sort of like you're going to compromise with synchrotron versus lab diffraction. If you got the right experiment, you know, sort of this is again one of these you're never going to see massively fast, you know, reactions. But if you got something that's of the right time scale, you actually do have a chance of seeing it. So this is basically a blank experiment, really. Sort of like this was just supposedly a very CO2 sensitive material. This was, that's just slightly sub-supercritical, so sort of like 950 psi CO2, 24 hours. You know, these are basically static snapshots, 30 seconds, and it does absolutely nothing. Just sits there and sort of like very boring. And it's one of these things that comes up. If you make the thing wet, this happens. Again, this is moly, because we had to get through the windows and the CO2 and sort of like everything else. 8-degree detector window. And here, we actually made the sample damp. And this is where you actually get a slight problem, because you've got water in there as well. So you start getting meniscus and a few other nasty things. So you've got a little bit of water to try and get through. And this is basically, this reaction is so fast under pressure that you just have no chance of seeing it on a lab instrument. Atmospheric pressure, you do actually have a chance. You can actually see some of the reaction going on. That's basically 3-second snapshots. As I say, you're never going to compete with a synchrotron as far as time resolution is concerned, but the right experiment can be done. You know, sort of like as long as your time's okay. Now, this is, as I say, is a glorified bomb. This is a new one. 300 bar, 300 there. This thing's heavy. This is where you start getting into size and weight constraints. This thing's about 10 kilograms as a full thing. So there's actually quite a lot of weight hanging off here. Moly's not good enough, so you're really having to go to silver at this point. This is basically just the setup. You know, you're going with silver. Necessarily, you're going to low angle, so knife edge is always going to be be sort of like necessary. And this is just I haven't actually been able to pressurize this. I'm not allowed to. I haven't got the safety clearance yet. But this is just an atmospheric SRM 1976. So basically your transmission is about 50% without material in it. Couple that with a PSD and you might actually stand a chance. This is some work by In Madsen, so I'm not doing all my own stuff. This is leaching of nickel laterites under autoclave conditions. So again, this is pressure. Want to use quantitative Rietveld analysis to follow reaction kinetics. This is basically designed by Paul Norby. This has been used on the synchrotron a number of times. And basically, it's a capillary reaction vessel. And so the sample can be a slurry or a solid. And it actually uses a pressure to actually drive liquid into the sample to actually start the reaction off, time equals 0, while it's actually in situ. And here it is. It's done in a lab as well. Again, one of these things that sort of like the capillary stage will have to be modified because you've got to oscillate it. It's obviously a pressure line. It can't be wound around a completely rotating sample, but oscillate it backwards and forwards. And just using a hot air blower, sort of like so nice and visible. They use the lab system for some of their work, so an INOL, MOLY. They've obviously got a large range PSD. And this is effectively the kind of data they get. And you see here that in cassiterite dissolution, you sort of like it starts to drop off on when you actually finish the heating, and the amorphous background decreases and then increases with the dissolution. So you get some of the information you want. Something a little bit different again, capillaries. These are organics. This is fairly standard stuff for single crystal people, but you have an issue with your cabinet. Drilling holes for a transverse line is not a good idea. So you actually put something inside the cabinet. You can put some of this stuff in. If you actually compress things into small enough, they will fit. Things are going to get a little bit tight. And you actually want to avoid icing during the summer. So you actually sort of also have to integrate the controllers with the diffractometer to actually be able to do complete ramp soak. The other sample problem is very corrosive, therefore sort of like glass capillary is not a good idea. Polymer capillaries. Now, this is often used at synchrotrons. Here, not actually quite as perfect because you're doing repeat quench and heating, so they end up like a banana. Sort of like the polymers, sort of like the actual vacuum that you start pulling as the thing sort of like will actually start distorting the polymer capillary. And that's the kind of data you can get. 52 data sets in 7 hours. You can do it completely automated, so I can go away and do something else. And as you say, this one's fairly boring. There's no phase transitions, but some others do. Variable counting. This was actually done. This is normalized, but sort of like the data was actually, there was a solution done. So we actually did this with a little trick for doing orientated data, but it can be done and sort of like refined using variable count. And for PSD, you can't do a continuous VCT, so it's effectively just chopping it into sections and changing the count time. In-situ humidity. You don't have to build it from scratch. You can just take something and modify it. They actually just replaced the sample holder and heater. Foil windows, so rather than thick beryllium, it basically means that you can use the lower energy radiations, so it's very material dependent, so they can use cobalt. And the trick here, in terms of relative humidity, keep everything isothermal, then you don't get any condensation. So I think they're on the 9th iteration of this particular one, and this is actually set up on a Philips. And they get quite good data. They can sort of like, this is very, very subtle changes in terms of what the relative humidity is. So this needs pretty close control. And this is actually basically iron sulfates, backwards and forwards. This is a new one, Electrochemical. This is a fairly one, sort of like transmission on synchrotron, reflection on lab systems. Each actually do have issues. Neither of them are particularly ideal. So we want the lab-based system, ideally. So Molly is handy. We want non-ambient. We're in Canada, therefore we want to do low-temperature work. And ideally, if you think about the geometry, a parallel beam would be nice, but sort of like, again, you need a mirror, which costs quite a lot of money, which we don't currently have. And effectively, that is what you end up with. This one's not pressure cell. This is actually quite easy to build. Sort of like it's just basically a machining and a lump of aluminium. So sort of like we didn't even have to buy the materials. The machine shop actually already had it. And I will give another plug for variable counting. This seems to be a topic of the moment. Sort of like this is just an illustration using some mineral which some people may recognize. Basically increasing the count time. And you can actually get also to optimize your sort of experiment time, increase the step with angle. Because you do get the peaks get broader at higher angle, so you don't actually need as many points to actually cover the peak. Conclusions. Pretty much everybody already had one, but sort of like they don't always really push it to a full potential. Don't necessarily just do what anybody else does. Don't be a sheep. Sort of like, use your imagination a little bit. And if the vendors don't sell it, build it. And as I say, it's possible to teach an old dog new tricks. So lab instruments have been around for years. In many instances, the concepts are the same, but there's nothing to stop you doing something new. Expect usability issues. They always crop up, and it's always the mundane things like you can't get access to a grub screw here, there, or everywhere. So expect things to take longer. And, as I say, complement synchrotrons. Don't try and compete head-on, because you're going to lose every time. But if you actually have the right experiment, you can actually, do good science. Sort of like if you're using a slow reactions, then a synchrotron might not be the best place to go to. And thank you very much.
Hi, it's Paul Smart from the University of Sheffield. I was just wondering, with your pressure line where you can't rotate your sample properly, do you have to apply any corrections to account for the fact that you're only oscillating rather than fully rotating?
That's not my experiment, that's Ian Madsen's, but theoretically, no. Basically, what you're losing on your particle statistics a little bit because you're not actually doing the full rotation. So that, in many instances, is going to be down to your sample preparation. So if your material's fine enough, whether Ian wishes to disagree with me, it shouldn't make a huge difference. You're losing a little bit, but as long as you've got enough rocking backwards and forwards, sort of like, it should be good enough.
We found when we do this at synchrotrons that if it stops and there's a grain in the beam, then you get some spikes as you're scanning through.
That's true, yes. Yes, but then again, sort of like if your sample's fine enough.
Yeah. Okay.
If you've got a very, very lumpy sample, then yes, your averaging is definitely an issue.
So grind
but
better.
I don't know how fine the sample was for that experiment because it's not mine.
Thanks.
Hi, Giulio Lampronti from University of Bologna. I have a silly question. First, do we use in normal lab experiments a capillary setting just to avoid preferred orientation? If that's so, do you have any experience with side-loading sample holders? And have you compared them, and do you have anything to say?
You can, this has been done actually a number of times. Side-loading sample holders don't tend to be sold. I don't know if there are any vendors. Do any vendors? No, Brochure doesn't. Side-loading. You can buy back-loading sample holders.
Okay.
So they're very commonly used for people with using clay minerals and everything else. But in many instances, people often do just buy their own. They help considerably, but they're not as good as a capillary. And it is very dependent on the person preparing the sample with the backloading or side loading. So it can be quite difficult to get it reproducible because you'll tend to always get some orientation left over, but it's not going to be the same every time. Unless you're very, very systematic in adding exactly the same amount of material every time, pressing it in exactly the same way. People sometimes use ground glass slides instead of just polished glass, so that sort of like it leaves a little bit of roughness to sort of like just you know, sort of like try and avoid it being perfectly orientated. But yeah, there's sort of like, if you want, we can discuss it. Other things like spray drying, and there's a whole, you know, as I say, sample preparation. You could fill almost a whole day, you know, for sort of like, you know, the various best ways to prepare samples for different experiments.
Okay, thank you.
The needles, yeah. 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 Our group does. You're talking about impedance. So presumably, are you trying to do simultaneous or? Oh, in high temperature? What, as a combined diffraction experiment or just separately?
Yeah, combined diffraction.
No, we haven't actually done that. It might actually be quite tricky to do because if you're using a pouch cell, yeah, it's sort of like it's potentially possible. But impedance is a bit of a black art to start with. You know, our group actually does quite a lot of in-situ impedance work for, you know, sort of like in terms of temperature and other things, but we've never done a combined experiment.
Ahmed Mohamed, Secondary University in Japan. Actually, thank you for your presentation. My question about if I want to buy new diffractometer and I want to do in-situ boundary diffraction, how I can choose my granulometer to be suitable for this experiment?
It depends. The problem is with laboratory instrumentation, it depends. You know, it often depends a little bit on the sample and everything else. One of my favourite setups, although it's very uncommon, is actually one with twin mirrors. It's a very odd one because you end up having two sets of mirror optics, so it's quite expensive. But you tend to get the advantage there from the parallel beam side to also getting some focusing, so you get a reasonable resolution as well. There is a downside to that, which I can explain to you later. But as ever, laboratory instrumentation is always a compromise. You gain on one hand by doing something, but you lose on something else.
Okay, thank you.
Hello, Henrik from Stockholm University. You were talking about PhD levels before, and have you any experience if the maximum value, since you're setting a minimum and a maximum, has any influence on the fluorescence?
Pardon?
The maximum value of the PhD level, you set it between two values, right?
Sorry, I didn't quite, between what
the
values?
PhD levels in...
the discriminators, oh sorry.
Yeah, the discrimination levels, yes. Has the maximum value any influence in your experience?
I tend to keep them sort of like symmetric on the peak. In any case, it's sort of like it has a little bit of an influence, but not a huge amount. But the thing is the high energy side, you also got Bremsstrahlung and other things. So there are reasons to, depending on your detector, to bring it down off the high end as well. But it's a case of fiddling. Each detector has its own characteristics. That was a particular Avantic detector. Scintillation detectors also have discriminators, and it's worth actually tweaking those. You can actually reduce the problem with those detectors. Silicon strip detectors, again, they have their own particular settings. So that's just one type of detector. But the principle is general.
So one last quick question, please.
Okay, good morning. Thank you for a great lecture. And I'm curious about the
What's your name, please?
Oh, I'm Carlos from Brazil, Federal University of Santa Catarina. And I would like to know a little bit more about your measurements with the accelerator detector and the refinements that you did.
Sorry, could you start from the beginning, because I didn't quite hear.
Oh yeah, just to know a little bit about the step size that you use, if you have some problems with the step size of the accelerator during the refinements, the Whitfield refinements, if you have some difficulties to make data conversion and so on.
Well, this is something you have to deal with at the data point, because it's one of these things that you cannot fix afterwards. I think the general rule of thumb, this is again something that crops up in data collection. Actually, the book that Kenneth mentioned yesterday on the data collection for structured solution actually does cover this in quite good detail, actually. General rule of thumb is you want the step size to be no larger than a full width half maximum divided by 5. So a one-size-fits-all experiment doesn't work. So you might have students in there and they use the same control file for everything. And sort of like it really often is not a good idea. If you've got very broad peaks from nanoparticles, increase your step size. If you've got very crystalline samples, reduce it. It's like that variable count one. I started off with a step size of less than 0.001. I don't normally do that. I only did that because that stuff is so absolutely crystalline that the peak widths were, extremely sharp. So you just always do a quick scan first, see what you're looking at, and then actually tweak your control files, whatever they may be, to actually get the best data you can in a time slot. If you're showing an instrument, you've booked an hour or whatever it is, you arrange it so you can get away with the longest count time possible with the largest step size you can manage to get the best data. If you use a step size of 0.01 for everything, you just get noisy data.
Let's thank Pam again for a nice talk.